Friends, how are you? Welcome to our beautiful channel Chem High. So in this video we are going to learn next important concept from solutions, that is the Henry's law. So what is this Henry's law? Applications of Henry's law and how to solve problems based on this Henry's law. So this Henry's law related to solubility, okay, solubility of gas in liquid. But before that, first we have to learn what are the factors affecting solubility of solid in liquid, okay. Factors affecting solubility of solid in liquid and factors affecting solubility of gas in liquid. That gas in liquid factor, based on that one law we are going to learn. That is a very important one, Henry's law, okay. So let's start. Solubility of solid in liquid. What are the factors affecting solubility of solid in liquid? So any solid is added to liquid. All solids are soluble in, all liquids are not, okay. So what are the factors affecting? Just three important factors. One is the nature of solute. Nothing but what solid we are adding. Nature of solute and solvent. Like this we can take. So nature of solute. Second one is the temperature. Temperature. And third one, pressure. Okay. So what is the effect of nature of solute and solvent? Temperature effect and pressure effect. So the first one is the nature of solute and solvent. In this we are learning one name, that is the like dissolves like. So what is the meaning of this one? Like dissolves like. What is the meaning of this like dissolves like? So nature of the solute, the given solute, nothing but solubility of solid, that is the salt solubility. This salt, ionic compound given or covalent compound given, first we have to check. So given compound is ionic. Ionic compounds means they are polar. Polar compounds are soluble in polar solvent. Okay, polar compounds are soluble in polar solvent. So if the given solid is ionic solid, ionic means they are polar in nature, they are soluble in polar solvent. The best polar solvent is water, okay, they are soluble in water. And covalent compounds, anyone given covalent, they are non-polar. Pure covalent compounds are non-polar. In covalent, some polar covalent compounds also there. Like that, polar covalent compounds given, this they are soluble in polar solvent and also non-polar solvent based on their interactions. Okay, covalent compound, it is a general statement. Covalent compounds non-polar, so they are soluble in non-polar solvent. Soluble in non-polar solvent. So like dissolves like. What is the meaning of this one? Like dissolves like. Polar soluble in polar, non-polar soluble in non-polar. So ionic compounds are soluble in polar solvents and covalent compounds are soluble in non-polar solvents. So like dissolves like. So it depends on nature of solute and also nature of solvent. The given solute is polar or non-polar and the given solvent is also polar or non-polar. Now the given option is all ionic compounds are soluble in water. This is right or wrong statement. All ionic compounds are soluble in water, like this given. Now ionic compounds. All ionic compounds are soluble in water or not? In S block elements, in second year group elements, we learned barium sulfate, insoluble precipitate, like that beryllium hydroxide, insoluble precipitate. Barium sulfate, this is ionic compound but it is insoluble in water. So why this is insoluble in water? So polar dissolves in polar, that is a general statement, like dissolves like. But the solubility of ionic and covalent compounds also depends on some other factors. So what are the other factors? This solubility depends on dielectric constant of solvent. So which solvent has a high dielectric constant? Then most of the compounds are soluble in that. Nothing but water is the best polar solvent. Its dielectric constant is high. So dielectric constant of solvent. And next it depends on lattice energy and also hydration energy. Solubility based on these two important one from second year group elements. Anyhow, we learned so lattice energy and hydration energy. So solubility also depends on like dissolves like polar compounds are soluble in polar solvent. Along with that, the solubility also depends on dielectric constant of solvent and lattice energy and hydration energy. So which solvent has high dielectric constant? That is the best polar solvent. So water is the best solvent for many compounds. Okay. Now lattice energy and hydration energy. What is this lattice energy and hydration energy? So anyhow, what is lattice energy? In chemical bonding, we learn this one. Oppositely charged gaseous ions. In bond-Haber cycle, this example only learned. Oppositely charged gaseous ions. Na plus gaseous ion and Cl minus. Oppositely charged ions in gaseous state. They are far away from one another. Now they comes closer and combines changes to 1 mole of crystalline solid. So during the formation of 1 mole of crystalline solid from oppositely charged gaseous ions that releases heat energy because formation of one solid. So interactions, attractive forces are developed. Attractive forces nothing but chemical bonding. Formation of chemical bond is always an exothermic process. Nothing but heat energy releases. Okay. So Na plus Cl minus combines changes to NaCl solid. Here it releases some amount of heat energy. That heat energy released, that is called lattice energy. So the minimum amount of energy is released during the formation of 1 mole of crystal lattice from oppositely charged gaseous ions. That is the lattice energy. Okay, this is lattice energy. Now this lattice energy generally is represented by U. Lattice energy is directly proportional to charge. Okay, and inversely proportional to size. Size of the ions increases, lattice energy decreases. Size increases, lattice energy decreases, and charge increases, lattice energy increases. Now this solubility, as the lattice energy increases, just to see the concept, lattice energy increases, nothing but releases more energy during the formation of the solid. So more energy release means that product formed is more stable. Yes or no? The product formed is more stable. So if it releases more energy, the product formed is more stable. If that is more stable, that is less soluble. So which one has more lattice energy? That is least soluble in water. Okay. So ionic compounds with more are covalent compounds. Also anyhow we can take ionic compounds with salts with more lattice energy are less soluble. Why they are less soluble here? Solubility is lattice energy is more, stability is more. Stability is more, least soluble. Based on this we can identify. So anyhow this lattice energy directly proportional to charge and inversely proportional to size. Okay, directly proportional to charge, inversely proportional to size. Now down the group. Second year group, because anyhow in first year group no exception, just down the group solubility increases. Second year group beryllium, magnesium, calcium, strontium, barium we are taking. Okay, in ionic form, nothing but +2 state you take. This forms the ion BaSO4 ion compound we are taking. So beryllium, magnesium, calcium, strontium, barium. Now down the group size. Charge anyhow similar. Size increases. Size increases, lattice energy decreases. Lattice energy decreases. So down the group, lattice energy decreases. If down the group lattice energy decreases, solubility increases. So down the group solubility increases. So which is more soluble? Given answer is barium sulfate is more soluble. Yes or no? But barium sulfate is least soluble. So this solubility also depends on hydration energy. So what is the effect of this hydration energy? Also depends on hydration energy. So what is this hydration energy? One ionic compound added to water. Okay. Now that becomes, for example, NaCl. It is added to water. It decomposes to Na plus and Cl minus. Na plus surrounded by water molecules. Like the Cl minus also surrounded by water molecules. Okay. Na plus surrounded by water molecules, Cl minus surrounded by water molecules. Now if any ion surrounded by water molecules, that ion is a hydrated ion. Now this is a hydrated ion. If any ion surrounded by water molecules, that is called hydrated ion. Okay. Now this is hydrated ion. Now which one surrounded by more water molecules, that is releases more energy. During the formation of this hydrated ion also, heat energy releases because surrounded by water molecules means here attractive forces are developed. Attractive force is nothing but chemical bonding. Chemical bond formation is exothermic. So this one also releases heat energy. That heat energy released is called hydration energy. So if any ion surrounded by water molecules, that ion is called hydrated ion. Hydrated ion releases a heat energy. That heat energy is a hydration energy. Okay. Now observe this. If the size is small, nuclear attraction is more. So because of more nuclear attraction, it attracts more water molecules. If size is small, that attracts more water molecules, it forms a large hydrated ion. If size is large, nuclear attraction is less. Because of less nuclear attraction, this is surrounded by less number of water molecules. If it is surrounded by less number of water molecules, small ion will form. Anyhow, this surrounded by more water molecules, nothing but it releases more hydration energy. It's surrounded by less water molecules, so releases less hydration energy. Nothing but down the group hydration energy decreases, size increases, down the group hydration energy decreases. Hydration energy decreases, solubility decreases. Hydration energy decreases, solubility decreases. So down the group what happened here, see that lattice energy decreases, solubility increases. But hydration energy decreases, solubility decreases. Now down the group, solubility increases or decreases, solubility increases or decreases. Now here. So anyhow in alkaline earth metals, second A group elements. Two important questions. One is solubility of hydroxides. Beryllium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide and barium hydroxide. Down the group solubility increases. Down the group solubility increases. Same group sulfates given. Beryllium sulfate, magnesium sulfate, calcium sulfate, strontium sulfate and barium sulfate. Down the group solubility decreases. The following is insoluble hydroxide. Very important question. That is the beryllium hydroxide. The following is insoluble sulfate. That is the barium sulfate. So in hydroxides, down the group solubility increases. What happens here? Down the group size increases. Size increases, lattice energy decreases. Okay. Size increases, lattice energy decreases. Size increases, hydration energy decreases. Size increases, hydration energy decreases. Lattice energy decreases, solubility increases. Hydration energy decreases, solubility decreases. Now here solubility increases or decreases? The decrease in lattice energy is more than the decrease in hydration energy. Okay, decrease in lattice energy is more than decrease in hydration energy. That's why here just we should consider lattice energy. So down the group what happened? Size increases, lattice energy decreases, so solubility increases. That's when hydroxide solubility increases. Now same group, lattice energy decreases, hydration energy decreases. But down the group, the decrease in hydration energy is more than decrease in lattice energy. The decrease in hydration energy is more than decrease in lattice energy. That's why no need to consider this lattice energy. Just hydration energy down the group decreases, so solubility decreases. Anyhow, this solubility depends on lattice energy, hydration energy and dielectric constant of solvent also. Okay, it is the nature of the solute and solvent. Nature of solute and solvent. So these two are important concepts here. And next one is a temperature. What happens? So solubility of solid in liquid, some are exothermic, some reactions are endothermic. For example, surf added to water, heat releases from that. Okay, heat releases. Nothing but if you touch that, it becomes hot. Okay, heat releases. And some other salts, for example nitrates, if these are added to water and if you touch that glass, nothing but beaker, then it becomes cool. So we can feel that. Nothing but that reaction is a endothermic reaction. So solubility of solid in liquid releases heat energy or absorbs heat energy. Two chances are there. So that is the endothermic reaction or exothermic reaction. Some salts, when they are dissolved in water, releases heat energy. From some salts, to dissolve in water, they require heat energy. Requires means they are endothermic and releases exothermic. So the solubility of solid in liquid, endothermic or exothermic. Two chances, either endothermic or exothermic. Two chances are there. Okay, solubility of solid in liquid. Now, if it is endothermic, what happens here? Endothermic, according to Lee Charles principle. For example, KNO3, NaNO3. Okay. And NaCl also we can consider here. KNO3, NaNO3, endothermic reactions. In endothermic reactions, according to Lee Charles principle, so we have to maintain high temperature. As the temperature increases, rate of reaction increases. Nothing but as the temperature increases, solubility increases. So if the reaction is endothermic, solubility increases with an increase in temperature. Solubility increases with an increase in temperature. If the given is exothermic, for example, CaCO3, Na2CO3, Li2CO3, these solubilities of these salts, exothermic. Now what we have to maintain? Low temperature. Here we should maintain high temperature. So here as the temperature increases, solubility in exothermic decreases. So we should maintain low temperature. For example, here they will give graph like this. Okay, this is very important one. It is the KNO3 or NaNO3. It is endothermic. As the temperature increases, solubility increases. As the temperature increases, solubility increases. And this is NaCl. NaCl also endothermic. This is endothermic. As the temperature increases, solubility increases. This NaCl also endothermic, but the change in that delta H is negligible. That's why we are getting like this. And what is this one? This is very important one. It is the Na2SO4. Here the temperature is 32.38 degrees. Okay, degrees centigrade. Na2SO4, 10H2O. What happens here? Na2SO4, 10H2O. What is the common name of this one? Na2SO4, 10H2O is called global salt. Now this one, 32.38 degrees. If this heated, now what happens? At 32.38 degrees centigrade, now it loses water. It changes to Na2SO4. Okay, Na2SO4 and H2O formed. Na2SO4 10H2O at 32.38 degrees centigrade, it changes to Na2SO4. Up to this, the process is endothermic. The process is endothermic. So in endothermic, as the temperature increases, solubility increases. Then this Na2SO4 decomposes to Na plus and SO4 2 minus. Now it's dissolved. Now it dissolved because up to that loses water molecules. So global salt, up to this, it changes to Na2SO4 and H2O loses. Then it dissolves in water. Now this process is a exothermic process. So what happens? Initially the process is endothermic. That's why as the temperature increases, the solubility increases. And then it is a exothermic. That's why again it decreases. So what is the transition temperature? 32.38 degrees. Okay. This is the effect of temperature, endothermic and exothermic. This graph is very important one. Okay, effect of pressure. What is the effect of pressure? So it is the solubility of solid in liquid. There is no effect of pressure. If it is gas, pressure affects. So it is the solid. That's why no effect of pressure. So pressure, no effect. Temperature given, endothermic. So now what are the factors affecting solubility of solid in liquid? Three factors majorly. One is the nature of the solute and solvent. Second one is the temperature. Third one is the pressure. Anyhow, this third one, pressure, no effect on solubility of solid in liquid. And temperature effect, two chances there. The given solid is the solubility of solid in liquid is exothermic or endothermic. If it is endothermic, as the temperature increases, solubility increases. If the given is exothermic, as the temperature increases, solubility decreases. Anyhow, in description box I given notes, link given. So in that notes I mentioned all the examples. Okay, you practice those examples. And next, first one is the nature of the solute and solvent. Polar dissolves in polar and non-polar soluble in non-polar. Nothing but light dissolves but it is not applicable for all the solids. Some ionic compounds, they are insoluble in water. That depends on lattice energy and also hydration energy. As the lattice energy increases, solubility decreases, but as the hydration energy increases, solubility increases. And like that, all covalent compounds are insoluble in water. This is also not correct. Some covalent compounds, they are soluble in water. That depends on hydrogen bonding. If they are able to form hydrogen bond with water, for example, ethyl alcohol, it is a covalent compound, but this compound is soluble in water. Why it is soluble in water? It can form hydrogen bond with the water. So which one can form hydrogen bond with water? Even though it is a covalent compound, that compound is soluble in water. Okay, these are the factors affecting solubility of solid in liquids. So now, what are the factors affecting solubility of gas in liquid? Solubility of gas in liquid. So here three major factors. First one, nature of gas. And second one, temperature. Third, pressure. Major factors affecting solubility of gas in liquid: nature of gas, temperature and pressure. So first one is the nature of gas. Which type of gases are more soluble in water? The given gas is easily liquefiable. That gas is more soluble. So what is the favorable condition? Easily liquefiable. How to identify which is easily liquefiable? Which one has the more critical temperature? Critical temperature means up to the above the temperature, gas cannot be liquefied. So that temperature is a critical temperature. Okay. Now, which one has a high critical temperature? That is a easily liquefiable. So if the given gas is easily liquefiable gas, that gas is a more soluble in water. Okay. So what is the favorable nature here? Easily liquefiable. How to identify? Definitely they will mention critical temperature. High critical temperature, easily liquefiable. Otherwise, if critical temperature is not mentioned, which gas can form hydrogen bond with water? That is also easily soluble. Otherwise, the molecule is large. Its van der Waals attractions are more. Van der Waals attractive forces are, because in noble gases we learned size increases, van der Waals attractive forces increases. That is, xenon is more soluble compared to remaining gases. Yes or no? So like that, size increases, van der Waals attractions increases, so solubility also increases. Okay. So anyhow, easily liquefiable gas is a more soluble. This is the nature of the gas. Which type of gas is more soluble given? Easily liquefiable. How to identify? High critical temperature. Not mentioned which can form hydrogen bond. Not identified which one has a large size, that has more van der Waals attractive forces. That is a easily soluble. From these three tricks, anyone we can apply. Okay. And next one is a temperature. Now, solubility of this gas in liquid is an exothermic process. This is exothermic. Exothermic means according to Lee-Chatelier principle, we should maintain a low temperature. So always we should maintain low temperature to increase the solubility of gas in a liquid. So temperature increases, solubility of gas in liquid decreases. Okay. Best example for this, take one bucket water. Okay. In this use the one heater. Dip one heater. Water heater. Okay. Just 5-10 minutes, not long time, 5-10 minutes heat that. After 10 minutes you remove this heater and just dip your hand. Okay. This upper layer hot, but this bottom layer cold. What is the reason for this? Upper layer hot but bottom layer is not. Okay. This is a cold. What is the reason for this? What happens here? Now, why hot water rises to up? Here in water many gases, oxygen gas dissolve in that water. That is nothing but dissolved oxygen. Yes or no? So oxygen. If the temperature is more, it is a hot water, temperature is more, the solubility of gases in that liquid is less. Nothing but here little amount of oxygen is dissolved, less number of oxygen molecules, otherwise less gases are dissolved in that. The gas content is less, nothing but its density is less. But here cold water, here more gases are, more gas dissolved in that. So more amount of gas dissolved, that means density increases. So upper layer hot, bottom layer cold. Why hot water rises up? The reason is its density is less. Why its density is less? In hot condition the solubility of gas in that liquid is less. That's why less amount of gas is present here, more amount of gas present here. So its density is more, its density is less. That's why here hot water, here cold water. Okay. Next, what is the effect of this pressure? So what is the effect of pressure? Now we are adding gas. Okay, we are adding gas. Gas dissolves in this liquid. Now if you apply the pressure, then gas molecules comes closer, then attractive forces increases. Attractive forces increases, then solubility increases. So if any gas is added, then apply the pressure. If you apply the pressure, the solubility of gas in this liquid increases. So what we have to maintain? High pressure. So maintain high pressure and low temperature. Okay, maintain the low temperature and high pressure. So what are the favorable conditions to increase the solubility of gas in liquid given there is a low temperature and high pressure, and the gas must be easily liquefiable. Okay, now for this effect of pressure, Henry given one expression. So what is that? Henry's law. So next one is a Henry's law. What is this Henry's law? As the pressure increases, solubility of gas increases. So at constant temperature, the solubility of gas increases with an increase in pressure. So if you are increasing pressure, solubility of gas, nothing but the amount of gas dissolved in given amount of a solution. The number of moles of gas dissolved in total number of moles of solution. Nothing but we are taking mole ratio. Mole ratio, nothing but that is a mole fraction. So the pressure is directly proportional to mole fraction. It is the Henry's expression. So the solubility of gas in liquid is directly proportional to pressure. As the pressure increases, solubility of gas in liquid also increases at constant temperature. Now remove this proportionality. P is equal to Kh into X. So P is equal to Kh into X. Here Kh is a Henry's constant. So what are the units of Henry's constant? What are the units of Henry's constant? Bring this here. P by X. X no units. Pressure units atmosphere. Nothing but Kh units atmosphere. Atmosphere or Pascal, like that we can use. So what are the units of Kh? Atmosphere. So in problem they will give atmosphere. Sometimes chance there. This is the solubility. Kh into solubility we are taking. Okay. Solubility means the number of moles dissolved in given kgs or given liters. Like this if given. Now Kh is equal to, bring this here. This is the atmosphere pressure by solubility means mole per liter. Nothing but what are the units? Atmosphere liter per mole. Yes or no? So they will give Kh value in atmosphere liter per mole. If like this given, you take pressure is equal to Kh into solubility. Solubility means the amount of gas dissolved in given amount of a solution. Okay, that is the solubility. Nothing but number of moles dissolved in a liter of solution. Then this type of units also chance there. So it is the units of a Henry's constant. Okay. What is the graphical representation of a Henry's law? So what is the graphical representation? It is like y equal to mx form. Okay, so now on y-axis we are taking P, on x-axis x. Okay, so no intersect. Now slope is equal to Kh. Okay, now if the given graph is shift this Kh this side, P by Kh is equal to x. P by Kh is equal to x. Now x, see it is just like otherwise you write x is equal to P by Kh. P into 1 by Kh. Okay, y equal to mx half. Okay, this is mxy. On y-axis mole fraction, x-axis pressure. Then also we are getting like this. Now slope is equal to 1 by Kh. Now this is not Henry's constant. It is a Kh star. Like this they will mention. It is a Kh star. So like this given, it is a Henry's constant. So what they given on y-axis, x-axis we have to observe carefully. On y-axis x given, on x-axis p given. Now slope is equal to 1 by Kh. It is the graphical representation of a Henry's law. Okay. What is the relation? Pressure is equal to Kh into x. Now solubility. Solubility is directly proportional to pressure. As the pressure increases, solubility increases. Now this solubility is directly proportional to temperature or inversely proportional temperature. Always we have to maintain low temperature. So solubility is inversely proportional to temperature. And this Kh solubility is directly proportional to Kh or inversely proportional to Kh. This expression Px is equal to P by Kh. Nothing but this solubility is inversely proportional to Kh. So solubility is inversely proportional to Kh. So as the pressure, three statements, important statements. As the pressure increases, solubility increases. As the temperature increases, solubility decreases. As the Kh value increases, solubility decreases. Okay. Now what is the relation between Kh and temperature? Now see this, these two. Kh is directly proportional to temperature. Nothing but KH value of any gas that depends on temperature. As the temperature increases, KH value increases. This statement also important. As the temperature increases, KH value increases. That's why in every problem at this temperature they will mention. At this temperature, this gas KH value is like this. Okay. Now, here in NCERT textbook also, one box given in that with values. Now values not required. So just NH3, CO2, O2, AR, N2, H2 and He. Okay, like this given. Now the order is a increasing order. What is this one? It is the Henry's constant value increasing order. So gas to gas, this KH value changes and temperature changes, KH value changes. These are Henry's constant values like this order. Okay, this order is important one. So ammonia least Henry's constant, helium highest Henry's constant. Which one has highest Henry's constant? Its solubility is less. So which is least soluble given? Helium. Which is more soluble given? Ammonia. So based on these Henry's constant values, we can identify the solubility. In options they will mention the values. So which is more soluble? Which is more soluble? Least Henry's constant value is there. Its solubility is more. Okay, it is based on Henry's constant solubility. These are the Henry's constant. Nothing but values we are not learning, just increasing order. Okay, so next, what are the applications of Henry's law? What are the applications of Henry's law and how to solve the problems based on Henry's law? Okay, applications of Henry's law. So the first one is deep sea diverse oxygen cylinders. So deep sea diverse oxygen cylinders, they will use deep sea diverse oxygen cylinder. Applications of Henry's law. The first one is a deep sea diverse will use a helium oxygen mixture instead of a nitrogen oxygen mixture. Helium oxygen mixture instead of a nitrogen oxygen mixture. Nothing matter here at this pressure, atmospheric pressure, what we are inhaling, that is the nitrogen and oxygen, because nitrogen percentage is more. So we are inhaling nitrogen and oxygen. But oxygen is soluble in blood. That nitrogen is insoluble. How that nitrogen is insoluble? See this, Henry's constant. This nitrogen, more Henry's constant. Henry's constant increases, solubility decreases. So in oxygen and nitrogen, which is more soluble at this atmospheric pressure in blood given? Oxygen is soluble, but nitrogen is insoluble. So here at this atmospheric pressure, we are inhaling that oxygen and along with nitrogen. But nitrogen not soluble, oxygen is soluble. But here for deep sea diverse, why we are using helium oxygen mixture instead of normal air? Nothing but nitrogen oxygen mixture, normal air. Why we are using this? Now deep sea, their pressure is more. Pressure increases. If pressure increases, what happens? According to Henry's law, solubility of gas in liquid increases. Nothing but this nitrogen can soluble. At that high pressure, this nitrogen can soluble in our blood. So their pressure is more in deep sea. That's why nitrogen soluble. Then nothing will happen. Say if it is soluble, then the person came out. Now here pressure is atmospheric pressure. Pressure decreased. If pressure decreased, solubility decreases. Yes or no? Their pressure is more. That's why nitrogen soluble. Now the person came out. Now here the pressure is less compared to that deep sea. Pressure is less. Now solubility decreases. Then this nitrogen is insoluble in blood. Immediately, how much nitrogen soluble in blood? That comes out like bubbles. So that effect, it leads to body pains. That effect name is a bends. What happens if nitrogen inhaled by the deep sea diver given? That effect name is bends. Nothing but body pains. That nitrogen total insoluble. That's why it comes out like a bubbles. It leads to body pains. That effect name is bends. So to avoid this, instead of that normal ordinary air, we are using helium oxygen mixture. Nothing but in this helium oxygen, nitrogen is also present at 11.7% nearly. In textbook that with percentage is given. Practice with percentage, so 11.7 to 11.2%. Helium we are using here. Okay. helium, oxygen, nitrogen mixture. So why we are taking helium, oxygen mixture instead of nitrogen and oxygen? In deep sea pressure is more, solubility of nitrogen increases. If the person came out, then the pressure decreases, so solubility of nitrogen decreases in blood. Immediately that nitrogen comes out. It leads to bends. To avoid this, we are using helium, oxygen mixture. So here what is the principle involved given? Pressure, solubility. Nothing but that is a Henry's law. So it is the application of Henry's law. And second application, cool drink bottles are sealed under high pressure. Aerated bottles. Cool drink bottles are sealed under high pressure. Why cool drink bottles are sealed under high pressure? Their carbon dioxide, aerated bottle, water, nothing but carbon dioxide dissolves in that cool drink. So to increase the solubility of carbon dioxide in cool drink, we have to increase the pressure. So cool drink bottles are sealed under high pressure. As the pressure increases, the solubility of carbon dioxide in that cool drink increases. That's why if you open that, immediately it comes like effervescence. Nothing but that how much carbon dioxide dissolved in that comes out, because we are if you open that, pressure decreases. Okay, so cool drink bottles are sealed under high pressure. If you open that, how much carbon dioxide dissolved in that comes out like bubbles. That is not like effervescence. Okay, so we have to seal the cool drink bottles under high pressure only. So solubility of carbon dioxide increases. Nothing but it is also application of Henry's law. Okay, and next one, mountain climbers. Mountain climbers, their thinking power is less. So long time if they are in mountain climbers, so if long time they are stayed there, then what happens? Deep sea pressure is high, and here atmospheric pressure, then their mountains pressure is less. Because of low pressure, for that mountain climbers, pressure decreases, solubility of oxygen in blood decreases. So less oxygen present in blood. Because of less oxygen, their thinking power decreases and they loses their memory and becomes weak. Loses their thinking power. That is anoxia. What is that effect name given? That is anoxia. What is this effect name? It is the bends. Okay, three very important applications. One is the cool drink bottles are sealed under high pressure, and second one is for deep sea divers we are using helium oxygen mixture, and mountain climbers thinking power is less because of less solubility. That effect name is anoxia. Nothing but pressure decreases, solubility of oxygen in blood decreases. Okay, now the given is hot water density is less than cold water. It is application of Henry's law or not? Hot water density is less than cold water. This option given. It is also application of Henry's law or not? What happens here? Hot water temperature is more. Density solubility of gas in liquid is less. So less gases are dissolved. That's why density is less. Okay. Now it is the effect of temperature, not the effect of pressure. Nothing but it is not a Henry's law. So if this option given, not the application of Henry's law. Okay. So hot water density is less than cold water given. That is effect of temperature, not effect of pressure. Okay. So it is not the application of Henry's law. And next one, in summer season, cool drink bottles are placed in water like this given. Nowadays we are using freezer, refrigerators, but in my small first standard, second standard, that time aerated bottles, cool drink bottles, nothing but soda, cool drinks, they will keep in bucket of water in summer season. Why we have to keep that cool drink bottles in bucket of water? What is the reason for that? What is the reason? So in summer season temperature is more. Because of more temperature, that soda means the carbon dioxide gas only, cool drinks anyhow. So carbon dioxide gas dissolves in that. In summer season temperature is more, that solubility decreases, that carbon dioxide comes out. To avoid that we have to keep in water, then temperature reduces. Okay, now it is application of Henry's law or not? This is also not the application of Henry's law, because it is the effect of temperature. So only effect of pressure given, that is the application of Henry's law. So these are the applications of Henry's law. Okay, so next how to solve the problems based on Henry's law. To solve problems based on Henry's law, already I written one problem here. If N2 gas is bubble through water at 293 Kelvin, How many millimoles of N2 gas would dissolve in 1 liter of water? N2 excess pressure of this much and KH value of N2 also given. So based on Henry's law, any problem given, first you write the formula. What is that formula? Pressure is equal to KH into X. Yes or no? Pressure is equal to KH into X. This is the formula. Now pressure given. What is the pressure? 0.987 bar. Okay. And KH value given. What is the KH value? 76.48. Given is kilobar now. So convert into bar because this is in bar given. This is in kilobar given. Into 10 power 3 into X. Okay, first we are finding X because we know these two, this one we don't know. So X is equal to 0.987 by 76.48 into 10 power 3. So divide this one, how much we are getting? So how much we are getting here? So it is equal to 1.29. 1.29 into 10 power minus 5. Okay, this is the X mole fraction we are getting. But question is not mole fraction, millimoles. First calculate moles. Mole fraction is equal to number of moles of solute by total solution. Yes or no? Total solution number of moles. Just once you check this mole fraction, this is very less. Mole fraction is of nitrogen is very less, means the number of moles of nitrogen given solution is very less. So we can neglect this number of moles here. Okay. So now what is the formula? X is equal to Na by Nb. What is the mole fraction? 1.29 into 10 power minus 5 is equal to Na by number of moles of this water. Number of moles of water, 1 liter of water given. So what is the formula for number of moles? Mass by gram molecular mass. 1 liter, nothing but 1000 grams. By molecular mass of that water, 18. It is equal to 55.5. 55.55. So just it is a 55.55. Na is equal to 1.29 into 10 power minus 5 into 55.55. Okay, just multiply this one. So how much we are getting here? It is equal to 7.17 into 10 power minus 4. Now check it. It is the number of moles. But question is the number of millimoles. Okay, number of millimoles. Convert into millimoles into 10 power 3. So it is equal to 0.717. So answer is a 0.717 millimoles. That's it. Very easy to solve. Just first write that formula. P is equal to KH into X. We know P value, we know KH value. Just find the mole fraction. Then you check the problem. What they are asking, mole fraction or not? Not mole fraction. Number of millimoles. We know that mole fraction is equal to number of moles by total number of moles. Then you check this X value, very less. Then it is a negligible. Otherwise, we should consider that definitely. Okay. Na by Nb. Now number of moles of water in 1 liter given. So 1000 by 18, 55.55. So by 55.55, number of moles of this nitrogen gas is equal to this into this. So we are getting into 10 power minus 4 moles. Direct that option also they will mention there. This is the moles only, but problem is the millimoles. So converting to millimoles. So answer is a 0.717. Okay. So next problem. The next problem. Henry's law constant of CO2 in water is this much. Okay. Pascal given at 298. Observe this. At the temperature they will mention because Henry's law constant depends on temperature. Temperature changes, this value also changes. This is at 298 Kelvin. Calculate the quantity of CO2 in 500. Quantity, amount of CO2 they are asking. Not number of millimoles, amount. Okay, 500 ml of soda water. And 2.5 atmosphere partial pressure of the CO2 also mentioned at the same temperature. Okay, now what is the formula? So Henry's formula P is equal to KH into X. Okay. P given or not given? 2.5 atmosphere. But one in Pascal, another in atmosphere. Last problem, one in bar, another in kilobar. Okay, convert into Pascal. 1.013 into 10 power 5 Pascal. Yes or no? 2.5 into 1.013 into 10 power 5 equal to KH value. How much given? The KH value 1.67 into 10 power 8. Henry's law constant, KH value 1.67 into 10 power 8 into X. So X is equal to 2.5 into 1.013 into 10 power 5 by 1.67 into 10 power 8. Simplify this one. So how much we will get here? This X value we are getting 1.51. 1.51 into 10 power minus 3. Okay, 1.51 into 10 power minus 3. 10 power minus 3, x value is less. So what is the formula? X is equal to number of moles by total number of moles. Then once observe this one, x value 10 power minus 3, nothing but it is the less value. So we can neglect Na here. So it is direct Nb. Nb means number of moles. How much given? 500 ml. So number of moles of this water is equal to 500 by 18. Yes or no? This is a half of that. 27.7 will get. Yes or no? 27.7. So x value 1.51 into 10 power minus 3 into this Nb. 27.7 is equal to Na. Okay? This is equal to Na. So here multiply this one, you will get the number of moles. So this number of moles we are getting here. And after number of moles, what we should calculate? Mass, quantity of CO2. Yes or no? So number of moles given. 1 mole molecular mass 44. So how much mass they are asking? Nothing but number of moles. Direct I am writing here only into 27.7 into 44 carbon dioxide. It is equal to mass. So how much amount they are asking? It is equal to that 27.7 into 44. Okay. Just you simplify this one, you will get the answer. That's it. So next problem. See the next problem. The solubility of N2 in water exposed to the atmosphere when the partial pressure is 593 mm is 5 point. Partial pressure 593 mm. The solubility of N2 is, okay, the sentence observe. The solubility of N2 is 5.3 into 10 power minus 4. Its solubility at 760 mm at the same temperature. Temperature constant. One pressure like this, partial pressure. At this partial pressure, this is the solubility. At this partial pressure, what is the solubility they are asking? So what is the relation? Partial pressure directly proportional to solubility. Mole fraction. Now we are taking solubility. Okay. So now P1 by P2 is equal to S1 by S2. Yes or no? So if two different partial pressures given, how to solve? Now what is the P1? 593 by P2 what they given? 760 is equal to S1 how much? 5.3 into 10 power minus 4 and S2 they are asking. That's it. So now S2 is equal to 5.3 into 10 power minus 4 into 760 by 593. Just simplify this one, you will get the solubility. Okay. If the question is solubility options, mole per liter like that given, per liter. Liter means how much? 1000 ml, 1000 grams by 18. Nothing but is a 55.55. What we are getting answer, that we should multiply with 55.55. Because the option is a mole per liter. Okay, mole per liter given. Moles they are asking, not direct like this. Yes, moles they are asking. But now the problem is just what is the solubility here. Okay, that's it. Only solubility they are asking. Simplify this, so you will get the answer. So now here, if partial pressure given, how to find the mole fraction, and in that mole fraction, direct mole fraction they are asking, or number of millimoles they are asking, or amount they are asking, or ratio they are asking. Anyhow, what we are using formula, any Henry's problem given, just the simple formula, partial pressure is equal to kH into mole fraction. Sometimes the chance is a partial pressure. Instead of partial pressure, total pressure of air they will mention. Total pressure of air. Total pressure of air is this much and mole fraction of nitrogen in air is this much. Calculate the mole fraction of that nitrogen in solution. Total pressure of that air given and mole fraction atmosphere given. Mole fraction of nitrogen in atmosphere given. Then what we should do? Partial pressure using Dalton's law of partial pressure. Partial pressure is equal to total pressure into mole fraction. First find the partial pressure. Then apply that partial pressure here. Don't take direct the total pressure. This problem I given in practice sheet once you observe that. Okay. So this is about the Henry's law. So what is Henry's law? What are the applications and how to solve the problems based on Henry's law. So in next video we are going to learn next concept, that is the Raoult's law. Okay. Thank you.